July 4th, 2012, the date of the announcement of the discovery that would crown the standard model of particles as the most successful theory of modern physics, and would explain why things have mass. That was the day of the discovery of the Higgs boson. But what does it mean? How does it work? Why does it look like a milkshake? This and much more you will discover now. Welcome to Nebula. To understand the Higgs boson, you must first briefly understand what the standard model of particles is. The universe is like a big Lego set, but made up of just 17 pieces that can be used to build anything. The distinction between these pieces is called the standard particle model. They are divided into two groups, fermions and bosons. The fermion group is made up of 12 particles, which are in fact the building blocks of the universe. Bosons, on the other hand, are the particles of the forces that coordinate and impose laws on fermions. These particles are called fundamental particles because they cannot be divided. Some examples of fundamental particles are the electrons and the up quark and the down quark, which constitute the protons and neutrons. Each of the fundamental particles arises from the excitation of its respective field. Don't worry about these terms, we will explain them now. The universe is permeated by various meshes, so to speak, which would be the fields. Every particle in the standard model has a field, which means that there are 17 fields permeating the universe in total. These fields have no mass, and it can be said that they are present throughout the universe at the same time, since, according to Einstein, the laws of nature are the same anywhere in space. When these fields are vibrated, a particle relative to that field is produced. For example, an electron is an excitation in the electron field, and an up quark is an excitation in the up field. At that point, scientists could already determine where the particles came from, but they couldn't say why they had mass, since fields don't have energy. Physicists arrived at this relationship because mass is energy packed together, as demonstrated in Einstein's famous equation, E equals to m times c squared. This equation relates the mass of an object to the amount of energy packed into it, and c squared is like a conversion rate between the two quantities, just as the conversion rate from the euro to the US dollar is approximately 1.09. The theory that tells us this is called unified field theory, and along with string theory and looping quantum gravity theory is one of the contenders to be called the theory of everything. The Higgs boson, also erroneously called the God particle, is not the brightest part of the discovery. In fact, the Higgs boson is a possible confirmation of the existence of the Higgs field. The last one is the real star of the show. What gives mass to a particle is the Higgs field. To understand this concept a little easier, imagine a milkshake with a cherry. The milkshake will be the Higgs field and the cherry any particle other than the Higgs boson. If you take the cherry and shake it in the air without contact with the milkshake, you won't notice resistance around it, just disregard the air resistance for better visualization. Now, when dipped in the milkshake, the cherry has a certain difficulty in moving because there's something that is limiting the movement, in this case, the milkshake. When the cherry is impregnated with milkshake, it is more difficult to move, and it may seem that it has more mass when it comes into contact with milkshake. The interaction between the Higgs field and a particle is very close to this. When a particle interacts with the Higgs field, which permeates the entire universe, it encounters resistance. This resistance is the mass of the particle. The Higgs field theory may also explain why light is the fastest known thing in the universe. The cherry used in the example would be a single particle among all of the standard model. Just as a cherry interacts differently than a sprinkle with a milkshake, an electron interacts differently than a photon with the Higgs field. A sprinkle is always going to be easier to move around a milkshake than a cherry. This explains why some particles have more mass than others. They interact differently with the Higgs field. The particle that least interacts with the Higgs field is the photon, the particle that makes up light. Because it interacts less with the Higgs field, light does not suffer as much from the resistance of this field. So the speed of light is the highest speed in the universe, and all light can reach it. Since all the work is done by the Higgs field, why is the Higgs boson important? First, let's understand what the Higgs boson is by continuing with the milkshake example. When you shake a milkshake too much, it can splash because of that shake. That splash is the Higgs boson. If we interpret each of the fields as different flavors of milkshake, the splash from stirring each of these drinks is the particle referring to that field, as stated earlier. The Higgs boson is hypothetical confirmation of the existence of the Higgs field, as every field has its particle. We say hypothetical because there is no absolute certainty if the particle found is really the Higgs boson, but the data collected so far points to confirming the identity of this particle as really being the Higgs boson. If the suspicions are correct, it would be great because a part of the theory would be proven. On the other hand, if the particle is defined as some other theoretical particle, it would make things even more interesting, as the standard model would have to be overhauled, leading to more and more discoveries in particle physics. But after all, how was the detection of the Higgs boson made? To identify not only the Higgs boson, but many other particles, the LHC, the largest particle accelerator in the world, was used. Particle accelerators are large pipes built in the shape of a circle. Inside them, atoms are accelerated to speeds very close to the speed of light, about 99.9% of it. After that, they are placed to collide with each other. This collision will result in the decay of these atoms into fundamental particles that are detected by mechanisms that monitor the interior of the particle accelerator. The Higgs boson is very difficult to study because of its peculiar characteristics. It is very rare to be obtaining these collisions, and it decays into lighter particles in a small fraction of seconds. It is for this reason that there is a lack of data about this particle, leading to suspicions that it is not what we think it is. Isn't it incredible to think that the simplest things in the universe, like a milkshake, a cherry, or a sprinkle, can be related to complex phenomena that are responsible for describing the laws of physics? One of the things that make humans different from the other animals is their ability to create relationships between the most varied of things to understand the universe around them. When teaching science, one of the best parts is undoubtedly benefiting from this human skill. So to help us continuing with this teaching, don't forget to subscribe to the channel if you like the video. With that, we say goodbye and hope to see you here in the next video. Thank you for your attention, and may the knowledge guide you.